Good morning. We got another hopefully quick-ish video for you today. And again, next week we'll start really reviewing a lot of stuff, going into more detail, especially with our first upcoming live lessons that we're going to do and recordings of those. So get your specific concerns ready for next week, like what's going okay, what's not going okay. So let's get started. So we have a company that's selling movies online and deciding how much to charge customers to download a new movie. Based on data from previous sales, the company predicts that if they charge X dollars for each download, then the number of downloads in thousands is 18 minus X. So I just want to sort of justify what this is actually telling you. So think about slope-intercept form. It starts at 18. So that means, let's see, the number of downloads, they're going to predict 18,000 downloads. But then that's going to go down by $1,000, or down by, 1,000. When they increase the price, because it's X dollars per movie, it's going to go down by 1,000 for every dollar they make the price of the download. So basically, they're getting a lot of downloads. But the more expensive that movie is, the less people who are going to download it. Like if X was 1, if they charged $1, they'd expect 17,000 downloads. Or if X was $12, more expensive movie, they'd only expect 18 minus 12 or 6 downloads. So that's what that comes from. That's not just like a random like expression that we just made up. That's somewhat reasonable predictions. All right. So we're going to complete the table real quick to show the predicted number of downloads at each listed price. So we're going to figure out all these various prices they could charge, and then the number of downloads they can expect, which is 18 minus X, and then the total predicted revenue. So the revenue is the money that comes in. So it's the money made. So they would make X dollars for each of these 18 minus X downloads. So the revenue is actually going to be, in this case, 3 times 15 is 45. So each of these multiply by each other. So go ahead, think about what would go there. Think about how you fill in this table, or go ahead and fill it in on your own on your Google Doc. So I've also moved over to Google Docs, so that way you can actually follow my formatting if you need to. So I just did whatever was in blue. So the $5 price, they expect 13,000 downloads. 5 times 13, 65. And then 8, 6, 3, and 0 were those differences. I just subtracted. And then I got revenue in thousands of dollars was 65,000, 80,000, 72,000, 45,000, and 0. If they charge too much, no one's going to buy it. All right. And just so you know, you can get these exponents in Google Docs. Let me see where it is up here now. I've zoomed in too far. Let's see. Where is it? I'll just search help for, it's called a superscript. Yeah, there it is. You can do it by pressing Command dot, or maybe it's in the format bar. Yeah, just do that. We're going to do Command dot to do another superscript. Like if I want to do up here, if I want to write it with an exponent and like not go to any menus, I can write 18 minus X Command dot, or if you're on another computer, it's probably some other different combination of keys. 18 minus X squared. I want a Mac, so it's Command for me. It could be Alt for you. You might have to search Superscript. All right. So basically, what we see here is that my expression of X times 18 minus X turned into 18x minus X squared. So we have this and this being the same exact thing. And I don't know why the red disappeared, but that's okay. So is this relationship between the price of the movie and the revenue in thousands of dollars quadratic? Well, we couldn't necessarily tell right here, but it is quadratic because the X term has an exponent of 2. So something's being squared. Or my variable is being squared. Alright, so we have that. So it's quadratic. So we expect to see a parabola graph, a U-shaped graph. We're going to graph it in just a minute. So we expect to see that nice U shape. So plot the points that represent revenue as a function of the price of one download in dollars. You can use desmos.com/calculator/you should because it's so much better. And let's just go to that right now. So we can actually use Desmos to plot points as well. So I'm just going to get a nice window going. I'll just zoom out. I forgot how much I actually need to zoom out. We're just going to plot some points. So we have, let's see, we're going to plot the points that represent revenue as a function of the price of one download. So that means that price is X and revenue is Y. Alright, so we're going to do 3, 45, 5, 65, 10, 80. Alright, so I'm going to plot those and we're going to see what that's going to look like. I'm going to order pairs over here, and I can do sort of side-by-side windows to show you. I have 3, 45 for the $3 price, got us $45,000. 5, 65, 10, 80, 12, 72, 15, 45, and 18, 0. So now I have to change my window because the graph, I can only see a few points. So again, let's see, my highest Y value is 80. So I'm just going to make my Y go up to like 90. And my X goes up to 18. I'll make it up to 20. So I have some points. All right, I've got that kind of up and down pattern I'm used to seeing. I'm used to seeing that parabola shape. All right, so now what we're going to do is, just to be extra, we're going to go ahead and plot the graph. So my function was, nope, function was untitled document, x times 18 minus x. Oh, geez, wrong window. Was x times 18 minus x. So all my points go right through that graph. But this just shows me all the possible combinations. So it turns out that this combination here, 9, 81, is very close to our point 1080, but 9, 81 is actually the point where they're going to make the most money. They get $81,000, and that was where they charge $9 for the movie. Yeah, $9 for the movie, and they get like 9,000 downloads. All right, so the graph actually shows us that maximum point very easily. We don't have to keep trialing and error things. So that's pretty cool. And Desmos is luckily going to be very helpful for us in this online unit graphic things because these are kind of annoying to make by hand. Notice we do have that still symmetrical curve, this parabola. An 18,0 over here is one of our zeros. It's one of our x-intercepts where the input of 18, if I charge $18, I'm going to get 0 revenue. The other 0, very interestingly, is 0. If I charge $0, if I have a free movie, I'm also going to make no money. So that makes sense. The other end of the spectrum is if I charge $18 for a movie, I'm not going to make any money because that's going to be too expensive. All right, so it's clearly not a Disney movie because those are very expensive. So, there's the graph, and let's see what questions we have waiting for us still. I don't think there's very many. Okay, let's see. What price would you recommend the company charge for a new movie? Well, we'd say $9 because they, here's a good word to use, maximized revenue at $9. They make the most money, 81,000, predicted by charging $9. All right, and the next part's a good thing to think about because it looks at how these graphs actually change. If the demand shifts so that we predict thousands of dollars, we predicted that. If we predicted, oh, it didn't translate well. Awesome. Let's see. If we predicted that was supposed to say 20 minus X thousand downloads. Sorry, Google Docs really hates my Microsoft equations. If we predicted 20 minus X downloads at a price of X, nope, at a price of X dollars per download, Let's say they're like, well, we underpredicted. Let's say that we're now going to get, we're actually going to get 20,000 downloads, but we're going to lose 1,000 downloads for every dollar we charge. What do you think will happen to the price that gives the maximum revenue? Do you think that they're going to charge more for this DVD to maximize revenue or less? So think demand has increased. They're now predicting 2,000 more people will buy the movie. Do you think they should raise the price to make more revenue or lower the price to make more revenue? So let's just see what happens. I'm going to take my graph. I don't have to zoom out a little bit because it's going to get a lot higher. I think it's going to be, that should be definitely fine. So now I'm going to change this 18 minus x to a 20 minus x. And you see my graph does go up a little bit. Not tons, but it goes up a little bit because it's my pattern from before. And let's see, where's the maximum? So they maximize profits there at $10 a movie. And they make $100,000. So even if they made only 2,000 more people buy it, or got 2,000 more people to buy it, their profits go up to 10,000 or 100,000 if they sold 10,000 DVDs. All right, so just showing you how that graph changes from 18 to 20. If it's 22 minus x, go up again. 23 minus x, 24 minus x. That was too many. 24 minus x. So it kind of changes, like, interestingly here. 1 minus x, 2, 3, 4, 5, 6. If I just keep changing that number, the graph kind of gets up and farther to the side. I don't think it really changes its wideness necessarily, but it definitely goes up into the vertex. You see is going up and to the right. It's pretty cool. Okay, so that's it for today's video. There's made 2 problems that pretty much work the exact same as this problem today. That's a lot. I have 1 more part that I'm doing handwritten today, and the rest of it is going to look just like that. All right, that's it for the week. Very good job. Stay tuned. Okay, last part of the movie is revisiting Tyler building a pen for his rabbit. We did this a day or 2 ago in one of our practice problems maybe, or in task statements. And we're just going to revisit it again real quickly so we can write more equations about it. So Tyler's building a pen for his rabbit on the side of the garage. So basically the garage is here. And he's going to use fencing to go here, here, and here. All right, because it makes sense to use an existing wall, so he doesn't have to build a 4th wall. He needs to fence in 3 sides and wants to use 24 feet of fencing, probably because fencing comes in multiples of 12 feet. I would want to do that too, so he's a pretty good consumer there. Good job, Tyler. Write an equation relating the width and length to the total 24 feet of fencing. All right, so give that a try. What equation could you write about length, width, and 24 feet? So it's kind of like perimeter, where we have 2 width plus 2 L's, but we only have 2 widths and 1 length. So width plus length equals 24, or 2 width plus L equals 24. Now we're going to solve this equation for length. So we're going to solve it for length. So basically, we're just going to take 2W plus L equals 24 and subtract 2W. And we get L equals 24 minus 2W. All right. You're going to follow a lot of these steps for most of your practice problems on this too. So make sure you're referring back to this part of the video. Using your equation from B, find the area equation of the pen. Okay, so area is length times width, right? But we know that length is 24 minus 2W. So area is 24 minus 2W times W. And so then we're going to distribute. We learned all about distributing yesterday, or the previous day. I've lost track of days of the week. So that area is 24W minus 2W squared. I'll write that bigger over here. And then we want to graph this, which, dang it, is online again. Did not think this through. That's okay. I'll go back to the computer. So we're going to graph this and figure out what length and width give the rabbit the most room. So graphing the equation from the pen problem, we know that area has to be 24W minus
2w squared. And the best thing about this calculator is it actually don't have to write x and y. You can just write in, and it'll figure out which one's the dependent. It knows that area is a function of width here, so you can just sort of like keep it in terms of a and w. So here's my graph. It even marks the vertex for you. Again, this calculator's awesome. You better get used to it. It looks like my vertex is at 672, which means my width has to be 72. I'll try it over here. No, width is not 7, width is 6. Independent. And then, oh dear Neptune, what did I do? I did something bad. Oh, it's because, yeah, okay. Okay. And then my area, don't write this in your computer, I'm just writing here because my paper's over there. And then my area would be 72. So, we know that the rabbit would have the most room if the width is 6, the area is 72, and if the width is 6, that would make my length have to be 12. Alright, so that's basically it for that problem. We just graphed it, we looked at our parabola, we looked at the vertex, which is the maximum point in this case. We'll deal with some parabolas that are U-shaped upwards. Honestly, most realistic applications have to do with downward parabolas like this. So you're going to find a lot of negative x squareds in word problems for parabolas, and that's just kind of the way it is, because gravity pulls things downwards. The relationship between like cost and profits. If you have a low cost, you have low profits. Medium cost, high profits. Super high cost, low profits. It's like that happy medium. So like a lot of parabolas are finding that happy medium. Same with this area. If it's 0 feet wide, the rabbit's got no room. If it's 12 feet wide, it's a long tank. It's a long pen that has no width. But some happy medium would be a more square-shaped area that actually has space to run around in. There's a lot of different applications, and most of them do have this downward shaped view. We'll probably deal with some that have the upward shaped view, but we'll have to cross that bridge when we get there. Alright, so that's it for today. Best of luck.